Hello from the world of industrial automation. My name is Artem Melnik. I am a software engineer with 15 years of experience in developing firmware and software for programmable logic controllers and integrating CODESYS runtime into this firmware. Let's develop an automated control system for an industrial dry heat sterilizer. All the mentioned devices are connected to each other through a router that has internet access. Our channel has the exclusive right to provide a promo code for a 35% discount on SPC210 and input-output modules from akYtec. I will provide all CODESYS projects used on our channel for free. After pressing the button, our own user authorization dialog window pops up. With one browser client, I logged in as administrator. With the second client, I logged in as BME. And with the third client, I logged in as nurse. On the third client, when I click the login button, I can log in as BMET and manage additional sterilizer settings. After 1 minute, the nurse and BME users will be automatically logged out. They will remain on the current page, but without the right to control the automated system. When they log in again, they will immediately return to the page they were on before the logout event. Also, our administrator can manage users by clicking the admin button. That means they can delete, add, and deactivate users, as well as assign them different permissions and change their passwords. In order to modify the control algorithm in just one file, I moved it into a separate library. To do this, I created an empty project in the library and added 3 components: Library Manager, Function Block, and Project Information. In the Library Manager, I added the standard library, since we use timer functionality in the algorithm. In the Function Block, under the var in-out section, I declared all the necessary variables and added the sterilizer control algorithm, where model-specific code will be executed depending on the model. For the project information component, I filled in all the relevant fields and installed this library in the library repository. It's important to note, when you use the yellow icon, the library will be installed along with the source code. Therefore, when the library is fully debugged, you need to save it as a compiled library, and then manually install the binary library file into the library repository. In the main project, I added this library to the Library Manager. Then, in all our PLC_PRG files, I declared an instance of the function block from our library and filled in all the references to our variables. Now we can edit the control algorithm only in the library project. I increased the number of sterilizers in the system to 9. The night sterilizer will be controlled by a separate task that I created. Let's demonstrate how all this works. In the browser, I connected to our system with 10 clients. As you can see, all 4 cores are almost idle when managing 9 sterilizer models. At the same time, there is data exchange with cloud and the web server with 10 clients connected simultaneously. Also, our control algorithm tasks are periodically executed on different cores of the PLC processor, since the scheduler tries to evenly distribute the load across all 4 cores. But we will configure the main task to be bound to any of the cores using Linux tools. If you compare the number of CODESYS tools to the number of Linux tools, CODESYS is just a drop in the ocean compared to Linux. I created Python source code to bind the task. In this file, the first input parameter is the name of the task. The second parameter is a bit mask for binding the task to any set of PLC processor cores. Using a built-in Linux tool, I bind a specific task to the specified set of cores. Next, in our CODESYS project, I added a library from akYtec to call Linux programs, and in the web_PRG program, I declared an instance of a function block from this library. I linked this program to the VisuTask task. In the algorithm, I added an expression where, depending on the set value, I will launch our Python program with the corresponding set of parameters. In main Visu, I added a drop-down list to which I linked the corresponding variables and list. As the event handler function for value changes, I selected the execute code function and added the appropriate expressions to launch the program on Linux. In the rectangle component, I linked the variable that will store the output of our Python program. Now, let's bind the main task to the fourth core of the PLC processor. As you can see, the Python program executed successfully and assigned the task to the fourth core. We can see the same thing in the PLC system console using the HTOP program. With this tool, we can now efficiently distribute any PLC tasks across the processor cores. If you are a professional web developer and want to create your own web panel using Python, HTML, JavaScript, and CSS, it's actually quite easy to do on this PLC. For example, in just a few minutes, I created my own custom browser visual component. Using all these technologies, I also made my own HMI panel in Python in about 5 minutes. And now I can create absolutely any visualization elements I want and not use, for example, CODESYS web visualization, or I can use them in parallel and integrate them with each other. As you can see, by using the library from akYtec and Python, I can use any built-in Linux core tools and solve absolutely any task in just a few hours, since there's an ocean of free ready-made solutions for both Python and Linux available online. What's also interesting is that you can rebrand the SPC210. For example, if your company develops software similar to CODESYS, you can order your own custom Linux core configuration and set of programs, as well as integrate your software solutions into this device. And, accordingly, you can sell it under your own brand with your solutions. What didn't we manage to do in the first season of videos? We didn't look at different models of PID control. We didn't implement fan speed control to reduce the duration of the cooling phase and the constant inertia of the internal temperature sensors, which directly affects the quality of PID regulation. We didn't consider the requirements for clean rooms. For example, to reduce the duration of the cooling phase, you can't release air into a clean room. Even though after sterilization there are no viruses left inside the chamber, but there may still be various dust particles and oxides. We also didn't consider models for regulating safe heating and cooling rates dependent on the type of sterilized instruments and their thickness. For example, when heating a sterilized instrument, its surface heats up faster than its cold center. So during the heating phase, the surface of the material expands, causing the center of the material to stretch while the surface compresses. During the cooling phase, the opposite happens. When cooling, the surface of the instrument tries to contract, so the center of the material contracts and the surface stretches, since the surface cools faster than its hot center, which is trying to expand. And the thicker the material, the greater these stresses become. That is, they become more dangerous in both phases. For example, metal and glass are harder to break under compression than under tension, while wood, on the contrary, is easier to break under compression than under tension. Therefore, for metal, the safe cooling rate will be lower than the safe heating rate, since there's a higher risk of cracks forming on the metal surface during cooling. For glass, on the other hand, the safe cooling rate will be higher than the safe heating rate, because glass is a brittle material, and during the heating phase, there's a greater risk of cracks forming in the center of the glass than on its surface during cooling. And for wood, the safe cooling rate will be roughly equal to the safe heating rate, since the main goal of drying wood is to remove moisture, not viruses. Therefore, during the cooling phase, additional stresses appear in the wood due to shrinkage from moisture loss, where tension on the wood surface becomes dangerous. I'll move all these topics to the second season if you vote in the comments for the continuation of this topic. Otherwise, I'll assume you're not interested and there won't be a second season. But for now, I'm announcing the first season on the topic Martian Colony 2.0. In this video, we'll break down how to create a control system for a future Martian colony following Elon Musk's bold vision. From powerful architecture and vital requirements to real prototypes on CODESYS. I'll show which systems will be key to human survival on Mars and how they can already be implemented today. Our channel has the exclusive right to offer a 35% discount promo code for SPC210 and input-output modules from akYtec. To get this promo code, just send a personal message with the text promo code to any of my contacts, melnikartemg@gmail.com, WhatsApp, or Telegram at the phone number +1 904 505 6665, and I'll send you the 35% discount promo code in a reply to your message. You need to apply it to your card in the special promo code field. There's another nice surprise for those viewers who purchased SPC210 and send me the device's serial number in a private message. I will provide all the CODESYS projects used on our channel for free. And don't forget to subscribe to our YouTube channel so you don't miss the next videos, and give a like if you enjoyed this one. That's all for now. See you in the next video.